Hey, so I will show you a test bench and how to use it. And I'm also working on a exercise, and I'm doing it a bit different than what the book says. So this is the book I'm using. It's Mark Swolinsky or SWO on digital system design with VHDL. So it has a chapter on test benches. But it also shows you test benches throughout the book. That's the philosophy of this book. It shows you all the time, not just a single chapter. And you have an exercise here, which I'm currently... I thought was a good idea to show you test benches with. And maybe show you what it means to have a netlist in here. So you can see they want you to do a full adder. Not going to talk about what that is, but it basically sums three inputs. You see A, B and carry in. So you get a sum and you get also a carry. So you can see that where you have one bit high, like here and then here, you will get one out. If you have 2 bits high, then it will be the value 2 in decimal, and value 2 in decimal is 1 0 in binary, so you get carry 1 and sum 1. If you have 3 bits, then it's the value 3, so you get value 3 or 1 1. Anyway, so the easiest way is to do it by just saying A SOR B SOR CI for S, and for carry you can divide the table in two and say, okay, if A is 0, then we have an AND gate. You can see in the truth table that this is the pattern for an AND gate, because both of them, B and CI, has to be on to get CO high, and then you can look at only these 4 last lines. When A is high, you can see that we have an OR gate. So only one needs to be high, or 2 for it to be high. So that's what I'm doing in the test bench to test the model you're going to make in this exercise with a real answer or a facet. So what I want you to do is to derive S and CO using only AND and OR operators. Okay, so what can we do then? Okay, so it's very time consuming, so I will just show you quickly. So what you want to do then, if you look at S first, if you're only going to use AND and OR operators and the NOT gate, they don't say that here, but you have to okay, they say inverters here, okay. And then you're going to make a netlist. So you have to look at the netlist later. Basically, they want you to go from this full adder to AND and OR gates. This is the European way of drawing the American equivalents. And then when you have this design, you're going to the netlist. And then test. So then you try the model and check if it's equal or not equal to the facet, which is just the simple functions. So you look at wherever the input pattern is giving a 1 out. This theory is simply a sum of products theory. So for every product that gives a 1 out, will then have to have this pattern, A not, B not, CI, and the next one is not, so not B, so not A, B, not CI. Okay, so you can do that. Not going to spend so much time on this. Or you can go down here and you can try and well, actually I think I'll have to do this, so I'll just speed up the video, okay? Okay, this one, and then also I made a mistake in my test bench that I made, so or this model. So in the test bench you will actually get an error message, so that's fortunate actually. So, okay, we have these two, and then we want this one, which is 100, and then you have this one, which is A, B, C, I. And all of them are high. So you can see this is an OR gate already. You have this when these two are on, or these two, you have this one alone, and this one alone, and this one alone, and the rest is negated. And that's basically A SOR, B SOR, Ci. So this will be the faucet, and this will be the netlist. What components do we have? We only have AND gates, right? Sorry for the bad drawing here. We have SOR gates. Sorry, SOR, I mean OR, of course. So this is a set, and this is the A, and this is the B. And the problem with this now is that A and B is now confusing, A and B here, so let's just say it has these inputs. And then the last one is the inverter, the European sign for the inverter anyway. So how can we do this? We only have 2 inputs on the AND gates, so and these are 3 inputs. And what about the OR function? We have 4 products. Well, what you can do then is you can divide it in 2, like this. Alright, so I'm going to get another paper here. Yeah, so you can divide it in 2. Okay, so now we divide it in 2. And now let's also call this something. Okay, let's call this for S1 and S2. So what is the reason why I'm doing this? Well, so this is S, right? This is S. Now we have 2 inputs. This is going to be a big tree. So this is S1 and this is S2. And we can see we have another OR gate here. So this will be S3, S4, S5, S6. This. This. So this is S3, S4, S1, S3, S4, S2, S5, S6. So when you're making a netlist, every net in the circuit has to have a name. And for this task we are also going to call this OR1 gate, this OR2 gate, OR3 gate. So every instance of this model has to also have a name. Because they are components. Take my word for it. Yes, and now let's look at S3 alone. Well, we don't have 3 input AND gates. We only have 2 inputs, so we have to split it in 2, like this. So that will give us and 1 and then and 2. And the gate names anyway. So we need a AND gate that splits this one in two. Okay. On S3. Now we're just looking at S3. This is an AND gate. So the output is S3 and the inputs are A, B, not, and then CI. And this is just the input directly from the inputs, right? So you don't have to make any gates there, but we need a gate here for A not and B not. And so on. So you can go on and on and on, and in the end you will get a map like this. So let me show you in the code. Here you can see if we're going to make an OR gate, we need a port, an entity for this model. It has two inputs, X and Y, and in the book they say, I basically just copied this from the book, but they used bit because it's easier to demonstrate using bits like this. It's not the same example. And for the OR gate, D has an output also, so I used standard logic because it's better when I connect it together in synthesis, but I'm not going to do synthesis. So the output is X or Y, so that's all there is in the architecture or the behavior of this device. And instead of making many files, you can just bring in the library again and make another and use such that the compiler can see the library or the functions in the library. And then when you write entity one more time, you are starting a new entity. So it's a bit weird that you have to bring in the library again, but that's how it works. So here it's for the NOT gate, X not X equals Z. So basically just turn X upside down. So, and here we have the AND gate. It has two inputs and a set. So bring this in again. You see the AND gate. It has two inputs and then an output. So the output is X and Y. That's it. Now, if we're going to make the full adder, we need three inputs: A, B, carry in, and S, sum out, and then carry out. So that's what I have here. These are the inputs and these are the outputs. Now, the tricky part is, now we're going to wire all of this together. So this entity here is basically a top level for all of these small entity blocks that I've already made. So you're going to use them as components, and I don't have any component declaration here because I'm doing so-called direct instantiation of them. So you can see here you have the first OR gate is instantiated with calling entity and then the work library, and here you have the OR2 which directly refers to this entity and this architecture. And then, since this is a direct instantiation, we have pin association. So, okay, So you have direct instantiation, and we have port association. That means for this OR gate, which has this entity, which is X, Y, and Z, in this order, if you write a single name on every of these positions, you get X position, Y position, and output C position. So, now if we go back to the realization of S using AND and OR gates, you can see that the last, or the very first in this tree, is OR1. So you see OR1, and then you have S. Hell. Guess I made a boo-boo here. Yeah, no, it's correct. So let's look at this. So see here, I called it single 1, single 2, and then S. So the output is S. On this OR gate, which is 1, I just put a 1, so I differentiate this one from this one. So and then you have 2 OR gates behind that one, which again connects to the inputs of the previous one. So you can see the outputs of these 2 are connected to the inputs of this one, and so on. And I made a mistake, and I'm going to keep that mistake. You can also see at the bottom here I have the NOT gates to make AN, because so I made a mistake and I found it later, but it's very nice for the test bench. So if you look at test benches, we have a test bench here, the right side of the screen, for the timer. And basically what you do is that you instantiate the timer, and in difference to this design for instantiation, this is direct and this is not direct, so you have to bring in the components, you get to declare it inside the architecture here. So you just copy paste the whole port from the entity. And I also have timer B in this test bench. And you can see I instantiate timer A and timer B. And then I connect all the port pins to, or the entity pins on the port, to signals that I have in this test bench. And also you can see that this test bench has an empty entity, because it's not going to be used as a port of any kind or a module, so just internal signals. So when you have done that, you can then make a clock like this, and also have a slower clock for count, and then you can manually, if you want, you can manually flip bits like this. You just say inside a process, which has a long list of wait states, and then in the end, I'm testing a lot of things here from the datasheet. Just want to show you that at the end, if you write wait, the process will stop. If you don't, it will just repeat. So that's one way of doing it. This is very, what shall I say, hardwired or manual. The other way is to make an automated self-testing test bench. So let's look at that. So here we have the full adder design, and then it has a set of signals, and then it connects all these modules together in a port map. What's going on inside here is not important to us. What's important is this port. So I have a component to declare it inside the test bench, and you can see A, B and CI. And that's basic, just copy paste. And then you have a lot of internal signals, which is basically the same. I have a test pattern. The reason for that is that I want to do this automation. So connect the test pattern to the inputs A, B and CI. And then in addition to some output, I will then also calculate a facet, as you can see here. So S facet is A or B, or sorry, SOR B or SOR CI. And here you have for the carry. So here starts the stimuli process. And we have a for loop. I haven't talked about that before. So you can make it more generic than this. You can say instead of 7, you can use attribute to check how large this test pattern vector is, which is 3 bytes. 2 down to 0 is 3 bytes large. But anyway, I just say for I in 0 to 7, then loop, and here it ends. I calculate a value for every pattern, so you use casting to get the standard logic vector pattern that you want. So what you want is 0, 0, 0, 0, 0, 1, and so on, and then that's the sequence you want. And the way that you do that, you can do a for loop where you increment I and do a loop for every I, and then this function here will make the pattern for you. Also, you need to include the numeric standard library. So I take this pattern and I put it onto the inputs of the full adder. And here you can see the full adder has a port map, like here. There's also a port map on the left side. Basically connects the internal signals together with the port. So, and then we wait a little bit because it needs to be stabilized before I can copy it. And then when I waited a half period, you can see the period. There's no clock here, so no period. If the S which comes out of the full adder is not equal to S facet, which is calculated simultaneously, then we will increment the error counter, and then we also will report a fail. So I do this for S and CO, and you can also assert a 0. And then you have a report on the end here, and you can also tell it how severe it is. So this says image, not sure why. Yeah, it's a way of getting the ASCII value. So yes. So let's try and simulate it then. Model sim. Okay, so we have to start a new project, and I have done that, so I hope it's okay that I don't have to show you how to start a new project. And then you have to compile it. So we start the, let's make it full window. So we start the simulation. You have to find the test bench, then OK. So watch here, you can see that it so you can see that the simulator loads these modules. Then let's add the signals. Then let's run it for 800 nanoseconds. Then you will see, you can see what happens. So the test pattern is incrementing, like I said, and the test pattern is directly connected to A, B and CI. So this is the stimuli, and then it's the outputs of S. So let's bring the faucet up to the S. You can see that it follows, that means that it's correct, but here it's not. So I have a mistake in my code. And what happens there is we get a note, fail, S not correct, in this simulation. And the reason is because we have this report in our test bench. It's very useful. So this basically tests all possible combination of this combinatoric logic element, full adder. And if you double click it, you can see that the simulation tool in Model Sim will then point at this vector, so you can see where it fails. And in the end we also have a report which says how many times it failed. So that was also in the code down here. Number of errors and so I should actually have an if statement to check if the errors are 0 or not, but I haven't bothered. You can say like this, if error equals 0, then or not equals 0, then else report simulation successful, and then and if. So let's see if I can compile that. So this is the test bench. Okay, didn't work. Okay, let's see what's not working. And if near end, else. Okay, we're missing semicolon. I won't write it, so. Also sometimes I need to check the path up here because it changes. Now it should be semicolon. Okay, let's try it. It compiles. Do a restart. Then run it again. It breaks, so maybe it's not a good idea to do a report here, but anyway, you can see it says failure. It still says failure. Okay. Now let's fix that failure. So I found it to be here. I made some error. So I fixed it. Go back. Simulation or compile. Restart. simulation successful. So yeah, so that's the answers. If you can make a test script, it's basically not really yeah, maybe you can call it a script. It's still VHDL code. So I thought this was a great way of testing. It's really hard making self-testing test benches. So, and I'm not finished learning this, so there will be more ways of doing this. So, and the other things I've been working on is the timer, and I figured out I needed synchronize the count because it's asynchronous and it makes problems. And I'm going to do this report and found out this was not really the way of doing shift registers. And also I need to learn more about states machines, so that maybe I will make a video about that. And yeah, so that will be interesting. So I need to learn state machines now. I know state machines, but this one is more complex, so because this has a more complex sequential behavior than other modules, so it has been a bit difficult. But the timer is now actually finished in RTL, so I hope that was interesting. Thank you for watching. Bye.